Welcome to UVU CS3060 Lecture 5.9, where we give some examples of how OS scheduling is done on, or CPU scheduling is done on various operating systems. We'll discuss the Linux operating system scheduling model, some of the changes that have happened, the Windows scheduling, as well as Solaris scheduling. So let's start with Linux. Now, up through version 2.5 of the Linux kernel, they used something called the O1 scheduler, which was a fairly efficient scheduler. It did a really good job managing the processes and getting things done efficiently. The big problem with the O1 scheduler was that it failed to work very well on multiprocessor systems. It had a preemptive priority-based scheduling algorithm. It really had two priority ranges, or two classes, if you will, of priorities. It had time sharing and real time. Time sharing is your standard scheduling and with no guarantees. And real time was more of a soft real time. You had actual priority values that ranged from 0 to 140. And so in this particular case, the 0 to 99 range was for the real time, and the 100 to 140 was for real time, for what were considered nice processes. This would be considered the time sharing. We use the term nice to indicate these processes were nice enough to place themselves in a lower priority range. And users could change their priority to a lower priority nice value. They couldn't change it to a higher priority, though. That required administrative access. The way these would happen was each of these particular ranges, the lower the value, the higher the priority. And so as you have a higher value, you would get a larger queue and be able to do more work on the CPU. We considered the task runnable as long as it had time left in its time slice and it belonged in a specific queue. If that particular, and we called that the active queue. If it ran out of the defined time slice, it was considered expired and would be put on a second queue where it would wait for wait for all the active jobs to run. Once all of the active jobs were complete, it would actually change those two queues. The expired would become active, and active would become expired, and it would go through the whole process again. This was done generally through per CPU run queues. So you would have the two priority arrays, the active and expired array, per CPU, and that's for tasks. And so it was very hard to load balance. It was just simply didn't work very well on a multi-CPU or a multi-core system. Starting with version 2.6 of the Linux kernel, there was introduced what was called the Completely Fair Schedule, or CFS. This also had what you would consider two scheduling classes, which would indicate the priority of particular jobs. The real secret to this particular algorithm was that you didn't have specific time allotments that the quantum would work with, but it was actually based on the proportion of the CPU time with the number of processes that were available in the queue, all having a certain proportion of the CPU time, and then each process would get a chance to run with that basic proportion. Now, again, still we're working. They had two scheduling classes. The what would be considered the user space or the regular scheduling algorithm, and then the real-time scheduling class. Again, a soft real-time scheduling, but still very effective, much higher priority than any of the defaults. So it's a multi-level queue. You can create other scheduling classes so that you'll be able to prioritize other processes for different purposes. So there is a certain amount of granularity here. Again, we're dealing with this nice concept where processes have this nice value between -20 and +19. Lower values, of course, have a higher priority. So the highest priority would be -20. You usually started out at 0 as a process, and you could actually go down 19 values, or an administrator could push you up to this -20 range. But what this nice value would do is it would help you figure out the latency for that particular process. Basically, how long must that process wait, or what's the range in which that particular process must be run? So clearly, processes down in the +19 range would have a longer period of time that it could sit idle before it was woken up and executed. And the way all of this was managed was via what is called the virtual runtime of that particular process. The virtual runtime is calculated by keeping track of how long a job is actually running on a CPU. And basically, the lower this virtual runtime, the higher priority you would be, which is why we have the completely fair schedule. And all of this would be maintained through a binary search tree, so that the lower your virtual runtime, the closer to the left side of the tree your process would be, and it was easy to find processes that had low virtual runtimes. Here's an example of that binary tree where we have the process, or the task, I should say, with the smallest virtual runtime way down here on the left side of this balanced tree. It is a smaller value, and there would be a pointer to this particular node so that it can be picked very quickly, making it more of an O1 operation than simply doing the O natural log of searching through the tree every single time. And this shows the range of priorities with a particular nice value in the normal range, and then the real-time priorities that existed for the real-time priorities. So usually in a real-time priority, it was a very simple first come first served type situation, whereas in the normal it was a round robin. Now on to Windows scheduling. Windows uses, again, a priority-based preemptive scheduling algorithm. Seems like a fairly common thing for operating systems at this point. And it would do a multi-level queue based on the highest priority threads. Now, usually the thread was used in a non-preemptive state. Threads would run until they were a block, or they used their time slice, which would be a preemption, or they were preempted by a higher priority thread. So real-time threads can preempt for non-real-time, obviously, but this is the key here. There are 32 levels of priority in the Windows scheduling model. You have a real-time class that ranges from 16 to 31. Again, it is soft real-time. And then you have a more normal real not real time, but a normal scheduling class between priorities classes 1 through 15. Priority 0 was, of course, for memory management thread. Nothing else could run there. And there were queues for each priority. If you don't have any, if the thread is not runnable, it runs as an idle thread. And we can see here that the Windows 32 API defines certain groups of priority classes which a process can belong to. And then those priority classes can be given a relative priority within that priority class. Most processes that you start would have a normal priority class. So let's go ahead and highlight that. It would have a normal priority class and would also have a normal relative priority in that class. Now, how your process was configured, which class it was in, and what the relative priority was, determined the actual numeric priority class, the 0 through 31, that you were scheduled. So let's go ahead and take a look. And the time quantum that was used depended upon which class and how relative it was. And if your quantum expires, your priority would be lower, but never below a certain base. Now, if a wait occurs, the priority is boosted. So if that particular job is moved up, is forced to wait, then it would be increased in priority. Thus, we have a multi-level feedback queue. The foreground window, of course, was given 3 times priority boost, simply because that's the most interactive part of a Windows system. And then we had user mode scheduling, which was an interesting creation that was added to Windows 7, where the application that creates and manages threads can do this independent of the kernel and set its own scheduling. The UMS scheduler comes from languages like the concurrent runtime framework. So here's a list of the various Windows priorities. Again, we have the classes of we have the classes of various Windows priorities, and then we have the relative priorities for those classes. And you can see where the numeric location was for these particular processes. So, for example, if your process is started in the normal class with normal relative priority, you would be that process would be put in the 8th queue, or queue number 8. You'll see that there is no 0 queue, just simply because the 0 queue is reserved for the memory management. What's interesting here is you can see that none of these queues outside of real time interfere with the actual real time queue. None of the normal queues actually go beyond even the real time's idle queue. Everything is a maximum of 15. And then everything above 15, 16 to 31, is reserved for the real-time class. So let's talk a little bit about the Solaris operating system scheduler. Again, priority-based scheduling. It has 6 classes. A time sharing, which is what normally everything falls under. You have interactive, real-time, system, fair share, and fixed priority. So, of course, a thread can only be in one class at a time. Each class has its own scheduling algorithm. And basically, time sharing is a multi-level feedback queue itself which has a loadable table that the system administrator can load up and make modifications to, if you will, fine-tune the scheduling algorithm. And so we find here that this is the dispatch table that we talk about, where depending on the priority that's given to a particular task or a particular thread, that particular thread's priority determines what the time quantum is for that particular process. So this time quantum is clearly very large for high priority jobs. It also shows that there's this time quantum expired value that is used in determining the scheduling, and also when it must return from sleep if the job has been put to sleep. And this gives a good idea of where between 0 at the lowest and 169 where the what the priority is for the various classifications. Clearly, the larger this number, the higher priority. And you want to deal with interrupt threads first. But then there's real-time threads, which take up a fairly large block. And then you have system threads. These are threads of particular functionality that helps maintain the system and keep it like garbage collection and such. Then you have the, if you will, the basic or normal threads where you have different priorities such as the interactive or the timeshare, all within the 0 to 69. And we have the order of scheduling depending on its particular priority. So the scheduler for Solaris actually converts this class-specific priority into per thread global priority in the number range that we saw, the 0 through 169. Threads run until, of course, they block themselves, until they use their time slice, so they're preempted, or they're preempted by a higher priority thread. Plus also, multiple threads at the same priority are selected by a round-robin scheduler. So most normal priority threads would run through the round-robin scheduler. This ends Lecture 5.9, where I talk about different operating system scheduling systems, or CPU scheduling systems on various operating systems.